Hi students, welcome to lecture online. In this session, we'll introduce you to a new type of follower. Before that, we'll try to recall what we have learned earlier, the different types of followers. So what we have learned earlier is a knife edge follower and a roller follower and a flat face follower. So all these three types of followers have an axis of reciprocation which is along this. These are due to the cam which comes in contact like this at each of these points, and they make this cam rotate. The rotation of the cam is now converted into the reciprocation of each of these followers. Now let us see what is an oscillating follower. Oscillating follower, as the name indicates, does not reciprocate. It actually oscillates. So for that it needs an inch, and in simple way you can assume this to be a lever type mechanism which has got hinged here, and this oscillates, and the motion from a cam can be transferred directly into this through a flat faced, or it could be transmitted through a roller. So in our syllabus and in most of the engineering colleges syllabus, we have the roller attached to the end of the oscillating follower, and here you see that each time a cam revolves like this, the oscillating follower would be lifted by this much. So the oscillating follower would be lifted through an angle here. So here you will see that here they would not give you the height of this, but they would give you the angle through which this oscillating follower would reach a new position from the lowest position. So if this is theta, so then if you want to know what is the extreme other position of the lever, then you should actually call it as h sine theta, assuming that these oscillate. Now the oscillations which actually go like this from here to here with theta, so this could be assumed as in the opposite side h, and this can be assumed as the lever length L. So in that way, if you want the h value, so h by L is sine theta. So if you want h is equal to L into sine theta. So if the values of the lever length and the angle through which this oscillating follower, which is basically a lever, has to move, that is this angle, and this is given, then you can find out h, which will be later used for drawing a follower displacement diagram. When compared to other type of followers, oscillating follower numericals have three unique data. The first data is the length of the lever, and then of course it has a roller with a roller radius, and then this is driven by a cam which has a base circle which is equal to this, and of course it will have some sort of a lift which this has to generate to produce an angle like this. And to locate this point, we should know the distance from the center of the base circle to this point. So this is called as the distance between the pivot point and the center of the cam. So therefore in a numerical, so if all this data are given, like the base circle radius is given, the roller radius is given, the lever length is given, then you can actually locate the pivot point. You can locate the pivot point this way. So first what you need to do is you need to draw a base circle. The center of the base circle is this. and then draw a vertical line, and then again draw a roller with the specified roller radius, and then since you know the length of the distance between the pivot point and the base circle center, with that distance you cut an arc. That means you measure the distance, through that's with the compass, and then you try to cut an arc. And again you know the lever length here, so you know the lever length which is equal to this. So from this point you try to cut an arc like this. So these two arcs cut here. So this is the lever. So this is the pivot for the lever point, and this is the distance. So this is how you start a problem in the case of a oscillating follower. Let us now solve a numerical, and you need a data. Let us see the possible type of data here. When we say the type of follower here, there could be 4 types: knife edge, roller, flat faced, and the oscillating follower. So we'll choose the oscillating follower, which we have not done. So the type of follower is the oscillating follower. And now the follower here has to move outward and also inward, and these are given in terms of the angle. Here the follower would move outward when the cam rotates through an angle of 20 degree is mentioned here. And of course the cam would rotate by an angle of 120 degree, and the oscillating follower would lift through an angle of 20 degree. And the way this has to be lifted, you can have 4 options here: uniform velocity, simple harmonic motion, uniform retardation motion, acceleration and retardation motion, cycloidal, like this. And similarly for the follower to return. So here let us make the problem simple. So let us take the follower to move outward through 120 degree, and also the return through 120 degree, and both, once it moves outward through 20 degree outwards, then it has to return through 20 degree inwards. We are speaking about the lever, that is the oscillating lever. Let the other required data are the length of the oscillating lever, and let this be 70 mm. So let me write this here, 70 mm. The distance between the pivot and the center of the base circle, let us take it as 80 mm. And then the base circle radius as 30 mm, and roller radius as 10 mm. So with this data, let us start to solve the problem. Before that, to know the distance through which the roller has to be lifted, we have to first draw a line with the length of the lever, and then we should draw a line at an angle of 20 degree, which is equal to the length of this roller, that is 70. And of course you need not have to do this Casper geometry, because we are trying to solve this with calculator. Now we know that the roller shifts from ear to ear, so therefore the vertical height which is actually displaced during this lever movement of 20 degree is nothing but h is equal to L, which is the lever length, into sine 20 degree. So let us now find, so this is 70 mm into sine 20 degree is equal to 23.94, which I will take it as 24 mm. So with this data, we'll start to draw the follower displacement diagram. We just now found that the height of the follower displacement should be 24 mm. So let us draw a vertical line which is 24 mm and then draw a rectangle like this. So let us take the first part, which is actually the ascent. Then no dwell is given in the problem, then there's directly descent. So for the next, so they directly have ascent and the descent here. So this is the ascent part, this is the descent part. And for the ease of the problem, let us assume that out of this data let us assume that the ascent is also UV, descent is also UV, which makes my construction easier here, because all this was taught to you earlier, how to actually construct for cycloidal and UARM. So it should not be a problem. So here, let us now divide this into 6 parts. Like this. The follower displacement diagram has only 2 parts. That is the follower ascent, which is actually phi a, which is through an angle of 120 degree, and we have seen that this height is 24 mm, and we have constructed as per this. And the follower rises through uniform velocity, so I am trying to draw a line. And if it was simple harmonic motion, then a semicircle here, and then dividing it by 6 parts and naming it so on. And similarly for cycloidal and for UARM, you need to follow the procedure. So this is the follower ascent. Then we have got the follower descent again through 120 degrees of the camera revolution. So no dwell in between. So this descends. So basically, there are actually 6 positions in between 0 degree and 120 degree. So let me name these positions as 1, 2, 3, 4, 5, 6, and this will continue this as 4, 5, 4, 3, 2, 1 and 0. Now I marked the locations 1 dash, 2 dash, 3 dash, like this up to 1 dash. So these are the heights through which the follower has to rise after every 20 degree, so that by this point it rises by 120 degree. That's at 120 degree it rises through this side, and again the next 120 degree it comes back to its original position. Now let us see how now we'll draw the base circle, which is equal to 30 mm, like this. And then let us draw the roller radius, which is equal to 10 mm, which is here, like this. So the roller and the base circle are now drawn. So knowing these 2 centers, then we need to locate the point at which the oscillating lever is pivoted. So as per the data, the oscillating lever length is 70 mm. So I'll take 70 here, and then keeping the roller, I draw an arc like this, and then it is given that from the center of the base circle to the pivot it is 80 mm. So I'll keep the compass here and then draw an arc here. So this locates the pivot point. So the pivot is here like this. The pivot initially is here like this with the roller, and this is the base circle of the cam. This refers to the starting position, which is at 0, where this roller is not lifted at all. So I should call this as the point 0. Now to locate the other points like 1 2 3 4 5 on the base circle. So we should start at this point, which is the 0 point, and then mark the angles for each of these degrees, like 0, from 0, 20, 40, 60, 80, because here this 120 degree is divided into 6 parts, so each of this is actually 20 degree. So I located these points. So once I have done this, then on the base circle, then I can locate these points here. So don't have to draw the radial lines. You just have to draw, keep the scale like this to locate these points. So of course, before locating this, here I have made a small mistake. So the mistake is the locations of the 0, 1 to 5 are not on this base circle, because for a roller follower, the trace point is not this point, the trace point is this point, because the cam can come in contact with any of the roller points here on the periphery. So what we should do is we should draw a circle passing through this, which is called as the prime circle. So each of the lines drawn for 20 degree where it cuts the prime circle. So let me call this as starting point as 1, this point as, this is 0, this point as 1, and the next point where it cut at 40 degree as 2, like this. All these are marked on the prime circle like this. Once these points 1, 2, 3, 4, 5 with reference to this are drawn, then we know that along with this roller, of course, here the roller is not actually rotating, the cam is rotating. But what we do in the cams is that we assume that the roller is moving, but the cam is still. So this is a relative velocity method. We can say that instead of considering that the cam is rotating, we are assuming this. So if this roller, which is here at the 0 position, if it doesn't lift as it comes to 1 position, this roller will be here. And where will be the location of the pivot? I can refer to this as the pivot. So let me name this pivot as pivot P0, because this refers to 0. And if there is no lift, as this roller comes here, where will be the pivot? The length of the pivot, the length of the oscillating lever cannot change. Therefore, you measure the length of the oscillating lever, which is 70 mm. So when the center of the roller comes from 0 to 1, the location of the pivot should be here. So before that, what we should have done is we should have known what are the possible locations of the pivot. So the possible locations of the pivot from the center, since we know as per the problem it is at 80 mm, we will draw a circle like this throughout, like this, at least to half the size, like 180 plus 90, around that 270 degrees. And then from here to locate this point, let us take this lever length like this, and then from 1 you actually mark it like this, and then from 2 you mark it like this, and again from 3 you mark it like this, again from 4 you mark it like this, again from 5 mark it like this, again from 6 like this. So as you try to do this, so you can continue further, but right now we'll solve for the ascent problem. So these are the locations of the pivot. When the cam rotates by 20 degree, it would go to 1. So this will be the pivot when it rotates by 20 degree. This will be the pivot 2. This is for 0, this is for 1, this is for 2. This is the pivot after rotating by 60 degrees. So this is for P3, like this. So we'll now write like this and show that these are the points which shows P4 and P6, P5, and we should, this is P6. So we have written this, all these pivots here. Once these pivots are drawn, then we can actually start. So this is the length of the oscillating lever from here, and as the cam rotates by 20 degree, so the new position will be at P1. So the path of this would be through this. So it would actually move like this. From P2 it would move like this. Of course you can see there is some small error in trying to do this because of the small mistakes that we do in drawing. So from P3 it would move like this. So you draw this axe so that you could locate the location of the rollers as it actually rises, because the way it can actually go up and down is along this arc, and therefore you have to draw this axe to locate this. Of course here you should actually you should keep this as this. I mean this is equal to the lever length, but here I'm trying to adjust this because the accuracy is not a big issue, but you should know the procedure. So this is the arc, and similarly from P5 you should draw equal to this, and from P6 you should draw like this. So these are the arcs. So once you have drawn these arcs, then you know that the distance that the roller has to cover after the first 20 degree is shown here, which is equal to this, very small distance. So this could be marked like this, and for the second one it could be done like this, and so you can continue like this. Here I mark all these points here, measuring each of these distances. So this, the height which I actually took it here, from 1 to 1 dash is this, from 2 to 2 dash this height is taken here, from 3 to 3 dash this height is taken here, and from 4 to 4 dash, and from 5 to 5 dash, and from 6 to 6 dash. So all these are the distances which we are transferring along the arc. So it is the absolute distance from this. Of course when we actually did this also here, this is moving around along an arc, but we are taking the height, vertical height. Here also we don't measure the length along the arc, we are only trying to take the perpendicular distance. So I think that actually minimizes the error. So once these points are done, then you need to draw rollers at each of these points. I will now draw rollers here. So once this is drawn, then I take the same roller radius here, and here the center of the roller is actually shifted by a distance from 1 to 1 dash here after 20 degree. So the roller center moves from 1 to 1 dash. So I take the roller here. I don't have to draw the complete roller like this because it takes a lot of time, and it's not easy, and it consumes a lot of time. So what I will try to do is that I will try to draw only the roller at the bottom like this. Okay, and then similarly like this I will try to draw from 2, and similarly here from 3, and from 4, and from 5, so what I am trying to draw is only the bottom of the roller. Of course people, if you have got a lot of time, then you can do that, but the time may not be sufficient for the other problems. So please be careful so you just need to follow the procedure and complete the problem. If you try to do it very neat and consume a lot of time in the examination, then you'll be losing marks. So like this you complete the rollers. So once the roller is complete, then to lift the roller by this height, the cam profile which was like this, so sorry, okay, it is the base circle, It is the base circle. The cam profile has to be like this to lift the roller by this much. Again, the cam profile has to go like this to lift the roller at every point. So what I try to do is I try to draw and curve like this through all these points here, like this. So this is how you draw the cam profile. So I only drawn the cam profile for the ascent part. Similarly, I will try to draw the cam profile for the descent part. Right now we have done up to the ascent part, that is this. This is the ascent part, which is actually 120 degree. We have done up to here. From now we have to again do it for 120 degree more. For that, what I do is I keep the protractor like this and start doing it. Marking for next 20 degree, 40 degree, 60 degree, 80 degree, 100 degree and 120 degree. So I marked it. Then I have to locate these points on the prime circle. So this refers to 6, this refers to 5, this refers to 4, this refers to 3 and so on. What I just said was ulta, so it is like it is going the other way from 6, 5, 4, 3, 2, 1 and 0 back. So very similar to this, where we actually try to draw the pivot points up to P6, we actually drew here, and we should continue this up to P0 again here. I had earlier located the pivot points P6 like this, so now I will continue. So I'll locate the pivot point P5, P4, P3 and P1 and so on, and I'll complete this. Mark this pivot points P3, P2, P1 and P0. Once this is done, you can draw the arcs which gives the probable locations along which the roller can move, like this, from each of these points like this. Of course, you don't have to draw an arc for 0, because finally it settles down at 0. After 6, 6 dash, so you have the next 20 degree, it goes to 5, 5 dash. So for this, you take the length of this like this. The accuracy is not a matter. So from 5 to 5 dash like this, and similarly 4 to 4 dash. And similarly 3 to 3 dash. Similarly 3 to 3 dash, and then 2 dash and 1 dash. Then we can draw the laurels. Once all these points have been located, then you can mark these points as 5 dash. This is 4 dash, this is 3 dash, 2 dash, 1 dash, of course this is 0, no lift. Then through these points, keeping the compass at these points, we will try to draw the rollers. So here, keeping the constant radius of 10, which is the roller circle radius, you draw arcs through each of these points, and of course at 0 it will be, the roller will be here, because there's no lift. So it's not easy to draw small rollers. very difficult. So try to complete these rollers, and once these rollers are done, to lift the rollers by this height, the cam profile should, the arc that you're trying to draw, which is the cam profile, should go tangentially through all these arcs of the roller, and it should go and meet the base circle. So out of this 360 degree, the first 120 degree is rise, the next 120 degree is fall or descent, the next remaining degrees is no lift. So this is dwell at the lowest position. So this is how you complete the problem given on oscillating follower. Here it almost takes around 45 minutes to 1 hour, even if you try to do it fast. So you can do it, you can actually speed up the process in two ways. The ways are, like when you're trying to mark these positions, since the heights are the same here, since the heights for 1 dash here and 1 dash here is the same, if you marked all these points at once, then you can mark 1 dash here and 1 dash here, like this. And also the other mistake I made is, of course it's not a mistake, it's a, people do it that way to try to save the problem. They first try to take the angle, so they will try to take this, I mean first after drawing the roller center and the pivot, the first pivot point, from here they will mark the angles first, like this, for the first 20 degree, 40 degree, like this. So these angles are actually 20, 40, 60, like this, they will try to mark, and then so they will try to take this as 0, and then they will try to mark these points like this. And once this is done, once this is located, from these points they will actually try to take this length of the lever like this, and then draw an arc like this, draw an arc which actually passes through this point. So in that way you'll be saving a lot of time in trying to locate this, so it will save a lot of time. Of course people have different ways of trying to do it, so in this way you can actually start like this. So first locate this points and then you can locate one, instead of actually locating 1, 2, 3, 4 at angles of 1, 20, 40 and 60. You can locate these angles as P1, P2 at 20, 40, 60, like this. Then from here, then since the lever length is known, then you can start drawing it here. Where it starts at the prime circle, there you can mark it as 1. From here you can mark it as 2, and that actually saves around almost around 3 to 4 minutes. So I should have actually done that way to save a lot of time. So I will actually post one more video which actually would teach you trying to solve in that way. Okay guys, this is a time when we have got corona pandemic, and people have their own issues, not able to connect to the internet, or maybe like you don't have instruments at home. So try to do something to come out of this. So this is a time where we have to learn in spite of this pandemic. So the corona may continue for still longer. So April 15th was the date of the lockdown. So until then, so it may continue even after that. So I request you to solve these numericals and scan this and upload onto maybe the Google Classroom, or to my, you can send it to my email ID, mbnacademics@gmail.com. Thank you guys.